Bismillahirrahmanirrahim. This is electric circuits course. For second semester students, and I am Dr. Khalid M. Hassan. Today's lecture is on node voltage analysis, and the textbook reference is chapter 3. I will select a few circuits in chapter number 3 for discussion on node voltage analysis. In the node voltage analysis, we use Kirchhoff current law, which states that algebraic sum of all the currents at a node is equal to 0. It means that if we have a node in a circuit, I'm not showing the rest of the circuit over here, there may be a current source like that. So we have a node, this is a node, and to this node, this is branch number 1, branch number 2, branch number 3, and branch number 4. 4 branches are connected to the node. So let us call it I1, this is I2, this is I3, and this is I4. As indicated in this current source, the direction is shown. We can assume that I3 is flowing away from the node, I2 is flowing away from the node, I1 is flowing away from the node. Algebraic sum means all the currents, sum of all the currents flowing away from the nodes is equal to sum of all the currents coming towards the node. So this is the Kirchhoff current law. We can write it as I1 plus I2 plus I3 minus I4 is equal to 0. In it, note that the sign of all the currents flowing away from the node is positive, while the sign of the current coming towards the node is negative. This is algebraic sum. Now I will delete everything to proceed further. And now I will select a very simple circuit so that you can understand it quickly. The circuit is very simple. We have a current source. This is an independent current source. We have a resistance of 4 ohm, a resistance of 8 ohm, and here we have 8 ohm resistance and another 8 ohm resistance over here. In this circuit, we have a node here, another node here, and the bottom node over here. We can put a dot over here, but this is not an additional node. So first of all, we identify all the nodes and we select a node as a ground node. So here we can select this node as a ground node. So the bottom node, at the bottom we have just one node. Putting a dot doesn't mean that it is necessarily a node. Now then we label all the nodes. Let us call it A, let us call it B, and this is our ground node. This is ground node. No need to write it because the symbol is already there. Now we see that number of nodes, if n is number of nodes, we have 3 nodes including the ground nodes, and in this circuit the number of node equations will be equal to n minus 1, means we will have two equations. One equation for node A and other equation for node B. We will write two equations for node A and node B. Now, in writing node equations, one method is to assume that all the currents are flowing away from the node for which we are writing equation. Presently, we are writing equation for node A. We assume that current through this 4 ohm resistance is flowing away from the node and through 8 ohm is flowing away from the node. Current source, when a current source is connected to a node, this is an exception. We will follow the direction of the current indicated in the symbol of the current. So this current is coming towards node A. Now, I will write node equation. So let us see what is this current. Current flowing from node A to ground node through 4 ohm resistance. Voltage across this 4 ohm resistance is VA minus the voltage at the ground node, which is 0 volt, divided by 4 ohm. This is the current flowing from node A to the ground node. We write it as voltage across the resistance VA minus 0 divided by the resistance, which is the current. Now, this current, the second current over here, this current is flowing from node A to node B, and we write it as current flowing from node A to node B. This is the voltage difference across 8 ohm resistance, and voltage divided by resistance is current. Now these two currents are leaving the node, and sum of all the currents leaving the node must be equal to sum of all the currents coming towards the node. So current coming towards the node through this current source is 2 ampere. We can simplify this equation by multiplying everything by 8. So this will be equal to 2VA plus VA minus VB, and as we are multiplying everything by 8, so the right hand side is 16. We can express this equation as 3VA, all VA terms, and minus VB is equal to 16, and this is our equation number 1 for node A. Now we write equation for node B. Again, in writing equation for node B, we assume that, as I have said earlier, we assume that all the currents are flowing away from this node. This is our assumption, and we follow this method consistently in writing all node equations. Now, the node equation for node B, what is this equation? What is this current which is flowing from node B to node A? VB minus VA is the voltage drop from node B to A divided by the resistance between these two nodes. This is the current flowing from node B to node A through 8 ohm resistance. There is another current over here flowing from node B to the ground node. So this is VB minus 0 divided by 8 ohm resistance. We can write VB minus 0. And the third current, which is also flowing from node B to the ground node, this is VB minus 0 divided by 8 is equal to 0. We can simplify this equation, as you can see, by multiplying everything by 8. And we have then VB minus VA plus VB plus VB is equal to 0. And combining coefficients of VA and VB, this equation can be written as minus VA and VB, VB and VB plus 3VB is equal to 0. This is our second equation. Now these two equations, equation 1 equation 1 and equation 2. These two equations can be written in a matrix form. We'll be solving these equations, and we prefer to express these equations in a matrix form. So first equation is 3VA minus 1VB is equal to 16. In matrix form, we will write it like this. This is the first equation, 3VA minus VB is equal to 16. The second equation, minus VB minus 1VB plus VA plus 3VB is equal to 0. Now we can solve this matrix equation VA VB is 3 minus 1 minus 1 3, inverse of this matrix, and 16 and 0 over here. I will solve it for you first time. So VA VB voltage matrix is equal to adjoint. In order to take inverse, the first we take adjoint 3 1 1 and divide by the determinant. So 3 multiplied by 3 9 minus 1 multiplied by minus 1, so 9 minus 1 is 8, and multiplied by 16 and 0. If we proceed further, this is 3 multiplied by 16 plus 1 multiplied by 0. Second row, 1 multiplied by 16 plus 3 multiplied by 0 and divide by 8, and further this is equal to 48, and this is 16 divide by 8, and finally this voltage matrix, this is equal to 6 and this is equal to 2. It means that VA is equal to 6 volt and VB is equal to 2 volt. We have solved these two equations. Now let us verify it. I will reproduce the circuit again over here. 2 ampere and 4 ohm resistance, 8 ohm, and then I have reproduced the circuit again. This was VA, this was VB, and this is the ground node. Now you see VA is equal to 6 volt, VB is equal to 2 volt. What is the polarity of 6 volt for VA? 6 volt means VA is positive, ground is negative. This way, this is the voltage drop from node A to the ground node, from node A to the ground node. VB 2 volt, 2 volt. So this is the polarity of the node voltages. Now we verify the Kirchhoff current law over here. Now I'll show you what is this current. This is 2 ampere. What is this current? The voltage across this 4 ohm resistance is 6 volt, and voltage divided by resistance 6 by 4. So this is 3 by 2 ampere as it is flowing away from the node. So this is shown at the right hand side. So this is 3 by 2 ampere. What is this current? This current is VA minus VB, means 6 minus 2, 4. 4 divided by 8. This is 1 by 2 ampere. So this is 1 by 2 ampere. Now Kirchhoff current law is satisfied at node A because the current coming towards the node is 2 ampere, and two currents, sum of the two currents leaving this node is also 2 ampere. Now we see node B. So at node B we see that this current of 1 by 2 ampere flowing from node A to node B. What is this current? Flowing from node B to ground node. The voltage across this is VB 2 volt, 2 divided by 8 ohm. So this is 1 by 4 ampere, And similarly, the voltage across this 8 ohm is also VB, means 2 volts, and 2 by 8 ohm is 1 by 4 ampere. Again here we see that 1 by 2 ampere current is coming towards the node, 1 by 4 ampere current leaving the node, and 1 by 4. So Kirchhoff current law is satisfied again over here. Now I'll show you, I'll discuss a very interesting aspect of the node voltage analysis. I will reproduce equation 1 and 2 over here. This is 3VA minus VB. I reproduced over here. 3VA minus VB is equal to 16, and the second equation is minus VA plus 3VB plus 3VB is equal to 0. I will express this as equation 1 as VB is equal to 3VA minus 16, and now I will plot this on two axes over here. This is VA and this is VB. Now in order to plot this equation, first of all, a quick way is to assume VA is equal to 0. So VA is equal to 0 means we are on the horizontal axis. When VA is equal to on the vertical axis, when VA is equal to 0, we are here. When VA is equal to 0, we are here. And what is VB when VA is equal to 0? From this equation, this is minus 16 volt. So VA 0 and VB minus 16 volt, let it be here. This is minus 16 volt. This is the point over here. VA 0, I repeat, and VB is minus 16 volt. The second equation, this second equation is VB is 1 by 3 VA. Sorry, again coming to the first equation over here. The first equation again, I forgot it. Now the second point in the first equation is what is VA when VB is equal to 0. So this equation over here, when VB is equal to 0, VA is what it will be, 16 divided by 3. This is 5.33. When VB is equal to 0 and VA is 5.33, it will be on VA axis. This is 16 and 8, and let this be 5.33. VA is 5.33 when VB is equal to 0, and if we connect these 2 points, this line will be representing equation 1 over here, equation 1. Now equation 2. In equation 2, this equation, when VA is equal to 0, what is VB? VB when VA is equal to 0. So this is equal to, this is straightforward, it is 0. So when VB is equal to 0, so we get only 1 point over here. And from here, just assume that VA is equal to 9. What is VB? VB is 3. So VA 9 and VB 3. So let it be, let this be 9 and VB 3 means, say this is 3, and we have another point over here. Now we connect these two like this. Where is the solution? The intersection over here, this is our solution. The value over here VA, which you can see is 6, and over here this is 2 volt, and VA is 6 volt. This is the graphical solution, graphical way to solve two equations. Note that if we write equation for the ground node, it will be a third equation, but this third equation will not add any additional knowledge to the existing two equations. So we will have only two linearly independent equations to solve two variables. Now I will select another circuit with two sources, and this time this circuit has one special thing in it. Resistance R2, instead of values, letter symbols are used over here. This is voltage source and this resistance is R3. This resistance is R1. We have one voltage source over here. Let us call it VS1, and a resistance over here R4. So over here I have selected this circuit from the textbook, and if you can see, it is figure 3.17 in 8th edition of the textbook. Now identify nodes. So this is a node, let us call it A. This is a node, this is B, this is a node, this is C, and fourth node is the bottom node, and we select this node as a ground node. In the circuit, if we try to write node equation for node A, we will assume all the currents are flowing away from the node. What is this current? It is VA divided by R1. What is this current? It is VA minus VB divided by R2. But what is this current? We don't know this current at this stage because there is a voltage source. In case of a resistance over here, we can find the current quite easily. So if I try to write, so again, this is VA minus 0 divided by R1. The second current, this current is VA minus VB divided by R2. What is this current? We don't know what is the current. Therefore, we assume a current over here. We use a letter symbol and let us call it IX. And we write it over here. This is node equation, and in this node equation you see that there is IX over here. We have assumed that this current is IX. Later we will be able to calculate this current. Let us write equation for node B. So just delete over here, and for node B we again assume that all the currents are flowing. Oh, what is this? We cannot determine the current flowing through this source. Indeed, there is some current flowing through this source in either direction, either downward or upward, but we cannot determine this current at this stage. We see that this voltage source, it appears between node B and the ground node. Therefore, we can see that VB voltage at this node at node B with respect to ground is equal to VS2, as the voltage source is connected across node B and the ground node. So this is equation for node B. Whenever a voltage source appears in a circuit such that one end of the voltage source is connected to the ground node and other is connected to any other node, voltage is directly known. Now, voltage equation at node C. At node C again, we assume currents, all the currents are leaving, but here current through this branch is IX. We have to stick to the direction of the current we initially assumed over here. So we will use the direction of the current, same direction of the current over here. And now if we write equation at this node, this current is Vc minus Vb divided by R3, this current plus Vc minus 0, the ground node, divided by R4, and these two currents are, this current is leaving according to our assumption, but this current over here, Ix, is coming towards the node. Now we have in these two equations, in this equation and in this equation, we can eliminate Ix. Eliminating Ix in these two equations, I will over here write this equation. This is Va divided by R1 plus Va minus Vb divided by R2 plus Ix plus this Ix, which is over here. So I will write it as plus Vc minus Vb divided by R3 plus Vc divided by R4 and is equal to 0. Now we have eliminated Ix, and how many equations we have now? This is equation with Va, Vb, Vc in it. This is another equation. Till now we have only two equations. How many variables we have? We have Va, we have Vb, and we have Vc. There are three variables and two equations. But if you look at the circuit over here, I will just delete unnecessary symbols in the circuits. And if you see the circuit over here, the voltage source, it appears between node A and node C. Due to the polarity of this voltage source, look at the circuit diagram, due to the polarity of this voltage source, we see that it is Va minus Vc is equal to Vs1. Yes, we have got third equation now. So equation 1, this is equation 2, this is equation 3. We have three variables and three equations. Therefore, we can solve these three equations easily. Now, over here, all three equations written in matrix form. Equation 1, no Va term, only Vb term, no Vc term, and in a matrix form, it will be written as over here. This is Va, 0 Va, then 1 Vb, then 0 Vc. This is equal to, what is the right hand side of this first equation? This is Vs2. This is the right hand side. Again, deleting unnecessary things over here. Now, equation 2, this equation. We have Va over here, the coefficient is 1 over R1, another Va plus 1 over R2. Okay, now coefficients of Vb, this is minus 1 over R2, this is Vb minus 1 over R3. Coefficients of Vc, this is Vc 1 over R3, this is Vc plus 1 over R4, and the right hand side is equal to 0 over here. deleting the unnecessary things over here. Now, third equation, this one, coefficient of VA, 1 VA, no V term, and this is the coefficient of VC, and the right hand side is equal to VS1. We can solve these equations using Cramer's rule or using any other methods. As I have discussed before, we can find VA, VB, VC over here. If this matrix is G matrix, so it will be G inverse over here, and this matrix will be VS2, 0 and VS1, and we can solve it. I will advise you to pause this video at this stage and write all these equations by yourself, just to check your level of understanding at this stage. This is very important. I will see if there is any typo in it. I think it should be okay. Now, I discuss another example, and in this example we have a dependent source as well. So this is this is a dependent voltage source, this 3 ampere is a current source which is independent current source. Just let me draw the circuits. 2 ohm and over here 4 ohm, and this is 8 ohm, and this is there is 4 ohm, and this is a dependent current source. Dependent current source, and the current flowing through this source is 2Ix. Where is Ix? In the circuit, the current flowing through this 2 ohm resistance in the indicated direction is Ix. So it means that if this current Ix is 1 ampere, the current flowing downward in this dependent current source, I will show it over here, this will be equal to 2 ampere. If Ix is 2 ampere, this will be 4 ampere. This is the meaning of a dependent current source. The current flowing through this current source is depending on a control variable Ix. Later we will discuss these dependent current sources in chapter 4 with more detail. Now, we identify nodes. This is, say, this is node A, this is node B, this is node C, and this is fourth node, and let us use this fourth node as a ground node. So, writing equations for node A, we assume, as usual, I said, currents, all the currents are leaving, so Ix is leaving the node, and the current leaving the node A through 4 ohm resistance and flowing towards node C, and one current is coming towards the node through this independent current source. So let us write node equation. So what is this current? Current flowing from node A to node C through 4 ohm resistance. what is this current? As shown, this is Ix. So at this stage, write it as Ix is equal to the current coming towards the node. This is 3 ampere. Now look at Ix. What is Ix? Ix is the current which is flowing from node A to node B through this 2 ohm resistance. So what is this current? So this is VA minus VB divided by 2 ohm. This is Ix. Now if I substitute this Ix over here and then I rewrite this equation, this will be equal to VA minus VC divided by 4 plus Ix. So Ix is VA minus VB divided by 2 is equal to, right hand side was 3. Now this equation can be simplified by multiplying everything by say 4. So this equation can be rewritten as VA minus VC plus 2VA minus 2VB, multiplying everything by 4, right hand side is 12. And we can write this equation again combining all VA terms. So this is 3VA, then VB terms, this is VB minus 2VB, and VC term, this is VC minus 1 VC, and the right hand side is equal to 12. So this is equation 1. Now write equation for node B. Now deleting all unnecessary things over here. At node B, we assume all the currents are leaving. Then all the currents are leaving. So the current leaving over here, the node B, and flowing towards the ground node. The current over here through 8 ohm resistance flowing from node B to node C. And at this stage, you can use the direction of Ix as the given direction of Ix, or you can assume that current is also leaving through this branch. Now, if I delete unnecessary things and I stick to my original assumption, we assume that all the currents are leaving the node for which we are writing equations. So I will write equations. What is this current? What is this current? So this is the current flowing from node B to the ground node. VB minus 0 is the voltage across 4 ohm resistance. What is this current? This current is flowing from node B to node C through 8 ohm resistance. And what is this current over here? What is this current? This is the current flowing from node B to node A through 2 ohm resistance equal to 0. Simplify this equation by multiplying everything by 8. So this is 2VB plus VB multiplying everything by 8 minus VC multiplying everything by 8. 4VB minus 4VA is equal to 0. Now again showing all the coefficients of VA, VB, VC together. So this is VA minus 4VA, VB terms 2VB, 1VB and 4VB over here, all VB term 3 plus 4, 7 and plus 7VB, and VC term, there is only one VC term minus VC, and the right hand side is equal to 0. This is our equation number 2. And now write equation for node C. At node C, we again assume current leaving. Current leaving, and due to the direction of the current of this dependent voltage source, if we follow, this current is also leaving. Now write equation for node C. So what is this current? This current is flowing from node C to node B. Remember, I'm saying current flowing from node C to node B. So voltage difference is VC minus VB, and this current is flowing through 8 ohm resistance. Now what is this current? This current, look at the circuit, this current is flowing from node C to node A through 4 ohm resistance. And the current over here, look at the circuit, the current flowing away from the node through this dependent current source is equal to plus 2Ix is equal to 0. Now we see this is Ix, and we already know that Ix is over here. So deleting all unnecessary things in the circuits, I will rewrite this equation. So first of all, I multiply this equation by 8 to simplify it. So this is VC, multiply everything by 8, plus 2VC minus 2VA plus this is 16Ix is equal to 0. Now I substitute Ix over here. So I write again, this is VC, VB plus 2VC, 2VA plus 16Ix. So what is Ix? This is 16Ix. Ix is VA minus VB divided by 2 equal to 0. And in here, this 2 and this is 8. And now writing this equation, first of all, I'll see where is VA. So this is VA minus 2 and this is VA, 8 VA. So I have 6 VA. VB terms, this is minus VB and this is minus 8 VB. So this is minus 9 VB. VC term over here. So this is VC and this is VC, and we have sorry, 3 VC. Right hand side over here is equal to 0. This way, this is our third equation. Now again, erasing all unnecessary things over here, just to make it clear. Now equation 1, equation 2, equation 3, writing these 3 equations over here, writing these 3 equations in matrix form, it is simple. So first equation is 3VA minus 2VB and minus 1VC in matrix form. Right hand side is, look at the first equation, right hand side is equal to 12. Second equation, minus 4VA plus 7VB minus 1VC is equal to 0. Look at the third equation. We can further simplify this third equation, divide everything by 3. So this is 2VA minus 3VB plus VC is equal to 0. This is the third equation, and therefore I will write as 2VA minus minus 3VB plus 1VC, and the right hand side is equal to 0. Again VA, VB and VC. So this can be 3 minus 2 minus 1 minus 4 7 minus 1 2 minus 3 1 inverse, and 12 0 0 over here. If we solve it, the voltages will be 4.8, 2.4 and minus 2.4. This 4.8 means VA is positive with respect to ground, and the voltage drop from VA to the ground is 4.8 volts, 2.4 volts. VB, polarity of the B node with respect to ground is positive, and the voltage is 2.4 volts, minus 2.4. The polarity of the voltage at node B is negative with respect to ground, and I will show you. This is minus 2.4 VC. So I will write it. Look at the circuit diagram. This is minus and plus, and this is 2.4 volt. This is the meaning of minus VC equal to minus 2.4. So now, students, we have discussed a few examples with current sources, voltage sources, all independent voltage sources and current sources, and with the circuits with dependent voltage and current sources as well. We have also discussed a circuit over here. Look at the circuit, this circuit over here. So in this circuit, there is a voltage source. There is a voltage source which appears between two non-ground or non-reference nodes. Node A is not a reference node, node C is not a reference node, and a voltage source appears between two non-reference or non-ground nodes. In solving this circuit, if you remember, we assumed that current IX is flowing through this element VS1, this current, and we used this letter symbol IX along with the direction for writing equation at node A. Look at the C node. While writing equation at the C node, we use the same direction of IX and in order to write equation at node C. So this is one method of applying node voltage analysis in circuits where we have a voltage source between two non-reference or non-ground nodes. If a voltage source appears between a node and a ground node, the case is very simple. The voltage at this node is directly shown over here due to this. So VB is equal to VS2. The textbook discusses a concept of supernode in order to address such problems. Supernode. And for this reason, I will take this circuit over here. I will take this circuit again over here. And just eliminate over here. The concept of, sorry, this is, sorry. I thought it is. I meant this circuit. Sorry, students. I meant this circuit over here, the supernode. I'll discuss it in the next lecture. Supernode, the concept of supernode, when a voltage source appears between two non-ground or non-reference nodes. So I'll discuss the second method of solving this circuit in the next lecture. Sorry for confusion with this circuit. So supernode will be discussed. The concept of supernode will be discussed in the next lecture, and I will advise you to follow the textbook to understand the concept of supernode so that you can easily understand it in my next lecture. So again, our next lecture will be on mesh analysis, or sometimes it is also known as loop analysis. And in mesh analysis or loop analysis, we will be applying Kirchhoff voltage law, which states that sum of all the voltages around a loop or mesh is equal to 0. So we will discuss it in the next lecture. Please note down all of your queries and questions, and on 16th of June I'll be available during the time slots mentioned in the timetable to address all of your questions and queries and difficulties. Please also give me feedback on the quality of this lecture, and if you feel some difficulty in understanding, so that I can improve it. I can address all of your reservations in the next lecture. Thank you very much.